Hello, I'm Ana Rodríguez and I'm going to talk about network slicing. Network slicing has been identified as the backbone of the rapidly evolving 5G technology. 5G networks offer multi-tenancy support and service-tailored connectivity, providing a top-notch quality of service, which will ultimately result in a long-lasting quality of experience. From now on, we are going to try to answer the question, what is network slicing? Network slicing in the context of 5G is a new defined concept introduced by the next generation mobile network. It facilitates multiple logical self-contained networks on top of a common physical infrastructure platform. New slicing builds on top of the following 7 main principles that shape the concept and related operations. Those are automation, isolation, customization, elasticity, programmability, end-to-end, and hierarchical abstraction. The next generation mobile network slicing concept can be seen in this scheme. The network slicing process is broadly broken down into 3 main layers, namely the service instance layer, the network slice instance layer, and the resource layer. Each service instance reflects a service provided by a vertical segment, application provider, or mobile network operator. The network slice instance represents a set of resources customized to accommodate the performance requirements of a particular service and may contain none, one, or a number of different subnetwork instances, being isolated or shared. A subnetwork instance can be a network function, a subset of network functions, or network resources realizing a part of a network slice instance. Each network slice instance is established end-to-end and may contain different subnetworks of distinct administrative and/or technology domains. The next generation mobile network also anticipates a number of emerging 5G use cases focusing on enhanced broadband access in dense areas, enhanced broadband access everywhere, high user mobility, massive Internet of Things, extreme real-time communication, lifeline communication, ultra-reliable communication, broadcast-like service, lightweight communication, and multi-connection. Some of these use cases impose diverse and often conflicting performance requirements, while others can be easily combined since the service requirements are similar. In this section, we are going to overview such fundamental virtualization technologies from the Prince of Network Slicing. In the first place, the hypervisor. It is a firmware which provides a virtual platform for guest operating systems, allowing applications and/or other services to be executed. Hypervisor enable and supervise the sharing of hardware resources between network slice instances. There are 2 main types of hypervisor. On the left, the type 1, referred to as a native or bare metal hypervisor, and on the right, the type 2, also known as hosted hypervisor. The type 1 are installed directly on the host machine's hardware, while the type 2 are installed on the top of the host operating system. In second place, the virtual machines and containers. On the one hand, in computing platform virtualization, the creation of a virtual machine provides the effect of a physical resource that runs its own operation system. On the other hand, containers are created based on the idea of an operation system level virtualization, where a physical server is virtualized to enable multiple instances of isolated servers to run as standalone applications. In the third place, software-defined networking. It simplifies network management, introducing programmability and open network access by decoupling the control plane from the data plane and via logically centralizing network intelligence. The software-defined networking paradigm is elaborated from the service perspective. A network slicing analysis is considered with every SDN client context, representing a potential slice as shown in the figure. By providing a set of network resource abstraction, resource groups, which also support control plane logic, form a functioning network slice. the SDN controller manages network slices effectively by applying rules when necessary and in accordance with the corresponding network policy. In the fourth place, the network function virtualization. It allows the deployment of originally hardware-based proprietary network functions on virtual environments, leveraging the cost efficiency and time-to-market benefits of cloud computing. The NFV architectural framework can be seen in the picture. At the top, the virtualized network functions that are software implementations of network functions deployed on virtual environments. At the bottom, the network function virtualization infrastructure, which comprise the logical environment's building blocks, in effect, storage, compute, network, and their respective assisting hardware components. On the right, management and network orchestration, that is responsible for managing and orchestrating VNFs and the NFVE. In the fifth place, cloud and edge computing. It offers storage, computational, and networking facilities within a single or multiple platforms for enabling a network slice. Such a basic infrastructure services can be offered by separate service providers, such as MapReduce, or as an all-in-one higher infrastructure service, for example, Amazon. Edge computing enables computing applications, data management, and analytics, as well as service acquisition in close proximity to end users, allowing a form of edge-centric networking which facilitates data proximity. It assures ultra-low latency, high data rates, intelligence, and control. The ETSI multi-access edge computing and fog computing are two of the most popular realizations. Now we are going to take a look to the network slice orchestration and management. Service management and network slice control consist of, on the one hand, service management layer that handles services operations like abstraction, negotiation, and service creation once a slice request is accepted. On the other hand, network slice control layer that provides resource abstraction to service management and handles network slice resource management as well as control plane operations. Where resource reconfiguration is not sufficient or latency cannot be fulfilled for assuring the desired service, the network slice controller contacts the service manager requesting an adjustment. The network slice orchestration architecture consists of four main parts. The first one, the end-to-end service management and orchestrator. It receives network slice requests from verticals and third parties and creates them. The second one, the virtual resource orchestration. It is responsible for virtual network function embedding and instantiation of the virtual network service graph, performing all related menu operations and value-added services. In the third place, the network resource programmable controller. It facilitates the flexible virtual network function service chaining, the quality of experience control, and the resource programmability, separating the control and data planes. And in the fourth place, the life cycle management performs legacy management, element management, and policy provisioning. The network slice broker considers a global network view based on the combination of network monitoring and traffic forecasting in order to assure resource availability, latency, and resiliency for the duration of a slice request. It takes care of the inter-slice resource allocation and selects a configuration policy to guide the allocated resources. Orchestration and life cycle management. Service management takes place in the service provider's domain, while the management of network slices is performed in the network operator's domain. Such a parting requires a business-to-business interface, the SLA. Based on this business relationship, a network operator can offer various levels of control to the service provider, such as monitoring only, limited control to compose slices from a catalog, or unextended control, where the service provider instantiates its own VMAs and menu stack. Finally, the network operator also administrates the phases of the lifecycle management of a network slice instance, what can be seen in the scheme. Those are preparation, instantiation, configuration, activation, runtime, and decommissioning. Finally, federated network slicing. There is need for exchange points that perform the resource negotiation between different administrative domains. The resources that form a federated slice may include cloud resources, which can facilitate VNFs and value-added services in a single domain or across different domains, as well as physical network functions and network links forming a multi-domain structure. All this takes us to the mobile network, which is divided in RAN and core network. On the one hand, radio access network slicing is emerging as a key enabler to flexibly customize and manage virtualized base stations while sharing the radio resources among them, with the objective of accommodating operators, service providers over the top, and service providers' requirements. On the other hand, the 3GPP has reshaped completely the core network by defining a more modular architecture wherein the main evolved packet core entities have been divided into granular network functions. In addition, it has adapted solutions such as ED Core and builds specifications, for example, network slice discovery and selection and network function sharing, to enable network slicing through the creation of core network instances for different types of services. Now we are going to mention some of the challenges and open research problems that are network slicing techno-economics aspects, RAN slicing and traffic isolation, slice security, slice optimality, Pareto optimality, user equipment slicing, and network slicing architecture evolution and APIs. That's all. Thank you for your attention.